All right, so this video is gonna build on the last one. It's basically how to calculate the least squared regression line, interpret the slope, interpret the y-intercept, and interpret the r squared value. Thought there was also nope, that's in the next one. All right, so we have the scatter plot from the last video. We already decided it's a strong negative linear association, and based on the video that was hyperlinked, we can assume that we can go ahead and proceed with our regression. So next step is calculate least squared regression line and sketch the line on the scatter plot. Thankfully, with modern technology, that's very easy to do. All you have to do, menu, analyze, regression, show linear. This is the linear that we want. This is algebra 1 stuff. We ain't there anymore. This is big boy stuff and big girl stuff. Sorry. So show linear. Since it's a linear regression, we can go ahead and assume we're going to use the linear one. And it gives us our y-intercept plus our slope times our x. It also gives us this r squared value here, which we'll get back to here in a little bit. So our predicted y, should be a y hat here, is going to equal 101.699 plus negative 1.8996x, which in context for our problem, if you remember, our x value is latitude and our y value is temperature. So our line, it's already sketched. There's the equation. I'm going ahead and write the equation out. 101.699 minus 1.8996x. So what this means is, remember, our y hat is our predicted y value, and our x in this case is our latitude. So another way we could write this, and probably the way we should, is the predicted temperature at a specific location in the U.S. equals 101.699 degrees, and this was Fahrenheit, minus 1.8996 x. And we'll get back to what those mean, because the next question is interpret the slope in context. So for this, here's our sentence stem that we like to use. Nope, not that one. I lied. Here's the sentence stem we like to use. This is our slope prompt. For every one blank increase in the x, there is a predicted blank decrease or increase in the y, depending on the situation. So all we have to do is go back and fill in these blanks. So let's do that. So for every 1 degree increase in the latitude, there is a predicted, what's our slope? I'm just going to write there is a predicted 1.8996 decrease in the temperature. And that's it. So, I don't know why I did that. It's pretty straightforward, right? All right, interpret the y-intercept in context. We have a prompt for that as well, y-intercept. So when x is 0, whatever our units are, the predicted y is whatever we got for our y-intercept and in y units. Again, x units in this case are our degrees in latitude, and our y units are our temperature. So this is easy enough. When the latitude is 0 degrees, the predicted temperature is, what was it? 101.699 699 degrees Fahrenheit. That's easy. This is why the units is so important, right? Because now let's think about what it is that we've written, right? According to our scatter plot, where's our scatter plot? We have all of these latitudes. They're in the U.S., but as you think about it, latitude is how far away you are from the equator, right? So the closer you are to the equator, the hotter it is probably going to be. We've talked about extrapolation, how you don't do that, but for what we have here, it does make sense when the latitude is 0 degrees. That would be when it is hottest, and it also makes sense that as we move away from the equator, the temperature decreases. The further you are away from the hottest place on the planet, the colder it should get, right? So far so good. Now this last bit, our R squared value. So there is another way to calculate this that we won't do. But we do need to know how to interpret it. R squared value is very similar to our R. It tells us, how strong our graph is. It tells us how much variation is in our Y happens specifically because of this particular X. So for our context, it tells us how much of the temperature change is specifically dependent on our increase in latitude, right? So we look at our little sentence stem. So R squared percent of the variation in Y can be explained by a linear relationship with the X. So our R squared was, in this case, where'd my calculator go? There it is, 0.601569. So I'm going to go ahead and write that so I can see that. R squared, there we go. Thought I was going to forget how to do that. Equals 0.601597. And in context, what that means, let's get our sentence stem back up here, is that about 60.16% of the variation in temperature can be explained by linear with, that's not how you spell it, with the latitude. And there you go, easy peasy. Now, real quick, I am going to show you that it is possible to get this and this, or essentially this equation, from the Listen Spreadsheets screen, because you may just want to do it that way. So when we go back to our Listen Spreadsheets, if we aren't feeling this, we want to see it and construct it ourselves along with some other stuff, we can use menu, statistics, stat calculations. Instead of two variable statistics this time, though, we can run a linear regression, and it can show us the data here instead. So again, we can pick our x-list as our latitude and our y-list as our temperature, and hit OK, and it'll tell us, okay, well, there's your y-intercept, there's your slope, there's the r squared. It also gives you the r. It also gives you all of the residuals, which we'll get to here in a little bit. That's a very convoluted thing, but that's about it. So there you go, very easy. Hope this one was helpful. Again, we have one more video in this little mini-series, so stay tuned for the last video in, I guess, chapter 2. Hopefully it's the last video, but here we go.